Picture this: a universe that isn't just expanding, but one that's racing outward faster and faster with every passing moment. Stars, galaxies, even the fabric of space itself, all accelerating into the unknown. It defies everything we thought we knew about gravity, about energy, about the very fate of the cosmos. And here's the wildest part: no one saw it coming. For decades, scientists believed the universe's expansion would slow down over time, pulled back by the relentless tug of gravity. But then, in the late 1990s, two teams of astronomers made a discovery so shocking it turned cosmology upside down. The universe wasn't slowing down at all, it was speeding up. Something mysterious, something invisible, was pushing the cosmos apart with unstoppable force. They called it dark energy, and to this day, it remains one of the greatest enigmas in all of science. What if I told you this cosmic acceleration is just the beginning of the story, that hidden within this mystery are clues so bizarre, they challenge our very understanding of reality? Over the years, researchers have uncovered 24 mind-bending revelations about this phenomenon, each one more surprising than the last. Some hint at entirely new laws of physics. Others suggest our universe might be just one of many in an unfathomably vast multiverse. And a few discoveries are so counterintuitive, they've left even the most brilliant scientists scratching their heads. This isn't just about distant galaxies or abstract theories. It's about the fundamental nature of existence, about whether space and time themselves might be far stranger than we ever imagined. So how did we get here? How did a simple observation about receding galaxies lead to a revolution in physics? And what do these 24 discoveries tell us about where the universe is headed, or if it might even have an end at all? Strap in, because we're about to embark on a journey through the most thrilling unsolved mystery in modern astronomy. From the mind-blowing evidence that first revealed cosmic acceleration to the latest theories that could rewrite the textbooks, we'll explore how each piece of the puzzle fits together and why some of them still don't. By the time we're done, you'll never look at the night sky the same way again. The cosmos is hiding secrets more extraordinary than fiction, and today we're pulling back the curtain. The story begins with the Big Bang, an explosion of space and time that flung matter outward in all directions. For most of the 20th century, scientists assumed this expansion would gradually slow down, like a ball thrown upward losing speed to Earth's gravity. Every galaxy tugging on every other galaxy should have put the brakes on the cosmos, but the universe had other plans. In 1998, two independent teams studying distant supernova made the same jaw-dropping observation. These stellar explosions were dimmer than expected, meaning they were farther away than anyone had predicted. The universe wasn't just expanding, it was doing so faster and faster, as if space itself had hit the accelerator. Imagine tossing a ball into the air, only to watch it rocket skyward with ever-increasing speed, defying gravity's pull. That's precisely what baffled astronomers. The leading explanation, a mysterious repulsive force dubbed dark energy, which makes up a staggering 68% of the universe's energy content. Yet here's the twist: we have no idea what dark energy actually is. It could be a property of space itself, a cosmic field that permeates the vacuum, or even evidence of an undiscovered dimension. What we do know is that its effects are real, measurable, and growing stronger as the universe expands. This revelation shattered long-held assumptions and forced scientists to rewrite the rules. The first mind-blowing discovery: the acceleration isn't just happening, it's accelerating the acceleration. Think of it like a car where the gas pedal sinks deeper on its own. pushing the speedometer higher with each passing second. Even more bizarre, if this trend continues, distant galaxies will eventually vanish from view entirely, their light stretched beyond detection as space stretches faster than light can traverse it. The cosmos might be headed toward a cold, lonely fate where civilizations of the far future would see only emptiness beyond their own galaxy, forever cut off from the rest of the universe. But how could something so counterintuitive hide in plain sight for so long? The answer lies in dark energy's subtlety. Unlike matter or radiation, its effects only dominate on cosmic scales, unnoticeable within our solar system or galaxy. It took the precision of modern telescopes to spot its fingerprints in the light of supernova billions of light years away. And with that single discovery, cosmology entered uncharted territory, one where the universe's ultimate fate hinges on an invisible force we're only beginning to comprehend. To understand how astronomers cracked the case of cosmic acceleration, we need to talk about nature's most reliable cosmic beacons, type Ia supernova. These stellar explosions are the gold standard for measuring vast distances across the universe, and here's why. Every type Ia supernova occurs under nearly identical conditions, when a dense white dwarf star siphons too much material from a companion, triggering a runaway thermonuclear explosion. Because the detonation always happens at the same critical mass, these supernovas shine with remarkably consistent brightness, like cosmic light bulbs of known wattage scattered across space. This predictability makes them perfect yardsticks. Just as you can tell how far away a light bulb is by how dim it appears, astronomers use the observed brightness of these supernovae to calculate their distance from Earth. But in the late 1990s, something didn't add up. Two separate teams, one led by Saul Perlmutter, the other by Adam Rees and Brian Schmidt, were studying these explosions in galaxies billions of light years away. Both groups expected to see the supernova appearing slightly brighter than expected, assuming the universe's expansion was slowing down due to gravity's pull. Instead, they found the opposite. The supernovae were fainter, meaning they were much farther away than any model predicted. It was as if someone had secretly moved the finish line during a race. The implications were staggering. The only explanation was that space itself had stretched more than anticipated over cosmic time, carrying these ancient supernovae even farther from us. The universe wasn't just expanding, it was doing so at an ever-increasing rate, propelled by some invisible force. This discovery was so revolutionary that all three team leaders shared the 2011 Nobel Prize in Physics. But here's what's even wilder. Type Ia supernova aren't just relics of the past. They're still helping us probe deeper into the mystery. Recent observations suggest subtle variations in their brightness that might hold clues about dark energy's true nature. Could these stellar explosions also reveal whether dark energy changes over time, or if it interacts with other cosmic forces? One thing's certain: without these celestial mile markers, we might never have stumbled upon the universe's best-kept secret. And as telescopes grow more powerful, each new supernova we observe adds another piece to the puzzle. The irony is beautiful. A dying star's final act became the key to uncovering the cosmos's accelerating fate. If you had asked any astronomer before 1998 what makes up the universe, they would have painted a very different picture. The cosmos, they believed, was dominated by matter. The stuff of stars, planets, and galaxies, all bound together by gravity's unbreakable pull. Even the mysterious dark matter, invisible yet detectable through its gravitational effects, was thought to play a supporting role in shaping cosmic evolution. But the discovery of cosmic acceleration flipped the script entirely. Today, we know dark energy isn't just part of the universe, it is the universe, making up a staggering 68% of its total energy content. To put that in perspective, all the galaxies, gas clouds, and cosmic dust we can see account for less than 5%. Dark matter, once considered the universe's hidden heavyweight, clocks in at around 27%. That means dark energy alone outweighs everything else combined by more than 2 to 1. Picture a vast, stretching rubber sheet representing space itself. Now imagine tiny weights scattered across it. These are galaxies, clusters, all the matter we know. For decades, scientists assumed these weights would slow the sheet's expansion as gravity pulled them together. But dark energy behaves like someone constantly tugging the edges of that sheet outward, faster and faster. No matter how much the weights resist, the harder gravity tries to pull things together, the more dark energy pushes them apart. This bizarre tug-of-war is etched into the Lambda-CDM model, the current gold standard of cosmology. Lambda stands for dark energy's mathematical symbol, while CDM refers to cold dark matter, the two dominant yet invisible ingredients shaping our universe's fate. What makes dark energy so perplexing is how it defies gravity's very nature. Instead of attracting, it repels a kind of anti-gravity woven into the fabric of space. Einstein actually predicted something similar a century ago with his cosmological constant, a term he later dismissed as his greatest blunder. Yet here we are, finding out the universe might have agreed with him all along. Even stranger, dark energy's density appears constant over time, meaning as space expands, more of it seems to appear out of nowhere. It's as if the universe is on a payment plan where the bill never comes due. But the real shocker is how recently this dominance began. Rewind the cosmic clock 8 or 9 billion years and matter, both normal and dark, would have been the undisputed ruler of the cosmos. Dark energy existed back then too, but it was a whisper in the background, overwhelmed by gravity's grip. Only when the universe grew large enough did dark energy's push finally overcome matter's pull, triggering the acceleration we see today. This cosmic power shift raises an eerie question. Are we living in a special era? The brief window where dark energy's rise is still fresh enough for us to notice. And if so, what other surprises might the universe be hiding in its deeper past or its distant future? The Lambda-CDM model fits the data beautifully, but it leaves one gaping hole: why dark energy exists at all. Some theories suggest it's the energy of empty space itself, a seething quantum foam of particles flickering in and out of existence. Others propose it's a new fundamental force, or even a sign that our universe is leaking into higher dimensions. But here's the twist: each explanation leads to another puzzle. If dark energy is truly constant, why does its strength match so perfectly with the critical density needed for cosmic acceleration? It's like finding a key that not only fits a lock but was seemingly designed for it. Could this be a clue to a deeper symmetry in nature, or just a cosmic coincidence? One thing's certain: dark energy's reign has rewritten the rules of cosmology, and as we'll see next, its influence doesn't stop at speeding up the universe. It might hold the keys to an even bigger mystery, one that could reshape our understanding of time, space, and the ultimate fate of everything. Einstein's greatest blunder might just be his greatest accidental prophecy. Back in 1917, while wrestling with his equations of general relativity, he introduced a mathematical term called the cosmological constant, a kind of anti-gravity force meant to keep the universe static, preventing it from collapsing under its own weight. At the time, astronomers believed the cosmos was unchanging and eternal. But when Edwin Hubble later discovered the universe was actually expanding, Einstein famously discarded the constant, calling it his biggest mistake. Fast forward 80 years and the jokes on all of us, his so-called blunder turned out to be the leading candidate for dark energy. Here's why that's mind-bending. The cosmological constant represents energy inherent to empty space itself, not the energy of particles or fields, but the energy of sheer nothingness, a concept straight out of quantum mechanics. According to quantum theory, even a perfect vacuum isn't truly empty. Subatomic particles constantly flicker in and out of existence, creating a seething foam of temporary energy. If you could tally up all these quantum fluctuations, they'd theoretically produce a repulsive force eerily similar to dark energy's effects. The math even fits mostly. When astronomers plugged the cosmological constant into modern equations, it perfectly described the universe's accelerating expansion. Einstein's discarded idea had come full circle, resurrected as the simplest explanation for the cosmos's runaway growth. But there's a catch, a colossal one. When physicists calculate how much energy these quantum fluctuations should generate, the numbers are catastrophically wrong. We're talking about a discrepancy of 120 orders of magnitude. To put that insanity into perspective, it's like predicting a single raindrop would weigh more than the entire observable universe. The measured value of the cosmological constant is unimaginably tiny compared to theoretical expectations, leaving scientists staring at what's called the fine-tuning problem. Why is dark energy's strength so delicately balanced? If it were even slightly stronger, galaxies would have been ripped apart before life could form. Slightly weaker, and the universe would have collapsed long ago. It's as if the cosmos won a lottery with odds worse than finding one specific atom in the entire Milky Way. This absurd fine-tuning has sparked wild theories. Some suggest an undiscovered symmetry in nature cancels out most of the vacuum's energy, leaving behind just a faint whisper, the dark energy we detect. Others propose the constant isn't constant at all, but a dynamic field that evolves over time, like an invisible cosmic thermostat adjusting itself. Then there's the multiverse angle. If infinite universes exist with random cosmological constants, we'd inevitably find ourselves in one where the value permits life. But these are Hail Mary passes, not satisfying answers. The cosmological constant's revival also reopened an old wound in physics, the rift between quantum mechanics and general relativity. Quantum theory treats empty space as a frenetic particle swarm, while relativity sees it as a smooth, bendable fabric. Dark energy sits at the crossroads, exposing how little we understand their marriage. Maybe the constant's weirdly small value hints at deeper physics, a hidden layer of reality where these theories finally reconcile. Or maybe, as some daring physicists argue, we've been fooling ourselves entirely. Alternatives like Quintessence propose dark energy isn't a constant at all, but a mysterious fluid permeating space, its density shifting over eons. Others wonder if Einstein's gravity itself needs tweaking on cosmic scales. One thing's clear, the cosmological constant's comeback is more than a historical curiosity. It's a glaring reminder of how much we don't know and how the universe loves to humble us. Just when we think we've got the answers, it tosses us a riddle wrapped in a paradox, and that's the thrill of it. Every unexplained digit in dark energy's value could be a clue pointing to physics beyond our wildest dreams. Just when you thought dark energy couldn't get any stranger, along comes its more sinister cousin, phantom energy. Picture this: not only is the universe expanding at an accelerating rate, but the force behind it might be growing stronger over time. Unlike ordinary dark energy, which remains constant as space stretches, phantom energy intensifies like a snowball rolling downhill, gathering mass and momentum until it becomes an unstoppable avalanche. If this eerie variant exists, it could lead to one of the most dramatic doomsday scenarios cosmologists have ever conceived, the Big Rip. Imagine a future where the cosmos doesn't just drift apart, but is violently shredded piece by piece. First, galaxy clusters would be ripped from one another, then individual galaxies torn asunder. Stars would be plucked from their orbits, planets ripped from their suns. In the final moments, even atoms themselves, the building blocks of matter, would be torn apart, their nuclei unable to withstand the overwhelming force of space itself, stretching faster than the speed of light. The universe would end not with a whimper, but with a deafening roar of space-time itself unraveling. What's chilling is that phantom energy isn't just science fiction. Recent studies analyzing supernova, galaxy distributions, and the cosmic microwave background have found that the data doesn't rule it out. In fact, some measurements hint that dark energy's repulsive force might indeed be increasing ever so slightly over time. It's like discovering the gas pedal in your car isn't just stuck, it's slowly sinking deeper on its own. The margin for error is slim, but the implications are colossal. If phantom energy is real, the countdown to the Big Rip could already be ticking. Of course, not all theories paint such a grim picture. Many cosmologists still favor the tamer cosmological constant model, where dark energy's strength stays steady, leading to a far less violent but no less lonely fate. In that scenario, the universe would keep expanding forever, galaxies fading into isolation as the space between them grows insurmountable. Civilizations of the distant future would gaze into a night sky nearly devoid of stars, their light stretched beyond detectability. But at least the cosmos would remain intact. The debate hinges on a critical question: does dark energy evolve? Phantom energy suggests yes, while the cosmological constant says no. Current telescopes can't yet measure the subtle changes needed to settle the argument, but upcoming missions like the European Space Agency's Euclid and a Nancy Grace Roman Space Telescope aim to hunt for clues in the ancient light of supernova and the large-scale structure of the universe. Their findings could either calm our fears or confirm that the cosmos is headed for a fate far more violent than anyone imagined. For now, the Big Rip remains a haunting possibility lurking at the edge of our understanding. It's a reminder that the universe's secrets aren't just about where we came from, but how it all might end. And whether the finale is a slow fade or a catastrophic rupture, one thing's certain: dark energy holds the keys to the cosmic curtain call. What if dark energy isn't a constant force at all, but something far more dynamic, a cosmic chameleon shifting its strength over time? Enter Quintessence, a theory so bold it reimagines dark energy, not as Einstein's static cosmological constant, but as a mysterious, evolving fluid woven into the fabric of space. The name itself is a nod to ancient philosophy, where quintessence referred to the elusive fifth element beyond earth, air, fire, and water. Today, it represents a fifth fundamental force, one that could rewrite our understanding of cosmic acceleration. Unlike the steady push of the cosmological constant, quintessence ebbs and flows, its density changing as the universe expands. Picture a balloon inflating not just with uniform pressure, but with patches of varying tension, some areas tugging harder, others softening over time. This flexibility could solve puzzles the cosmological constant can't touch. For instance, why did the universe's expansion briefly speed up during an early epoch called inflation, then slow down, only to accelerate again billions of years later? A static dark energy can't explain those shifts, but quintessence might. It's as if the cosmos has been riding waves of invisible energy, each crest and trough leaving clues in the arrangement of galaxies we see today. The hunt for this phantom fluid is already underway. Astronomers scour galaxy surveys like the Dark Energy Spectroscopic Instrument, DAISY, mapping millions of galaxies to spot subtle patterns in their distribution, fingerprints of quintessences push and pull. Others analyze the cosmic microwave background, searching for imprints of dark energy's fluctuations in the afterglow of the Big Bang. Even gravitational waves might hold hints, as ripples in spacetime could carry traces of quintessence's influence across the ages. But here's the real kicker: quintessence could bridge the gap between cosmic acceleration and quantum physics. Some theories suggest it's a cousin to the Higgs field, the quantum backdrop that gives particles mass. Others propose it's a scalar field, a kind of cosmic weather system where regions of high and low pressure dictate how space stretches. If proven, it would mean dark energy isn't just out there in the void. It's interacting with the quantum realm in ways we've yet to fathom. The stakes couldn't be higher. If quintessence is real, it would mean the universe's fate isn't set in stone. Its expansion could slow, speed up, or even reverse course down the line, all depending on how this enigmatic fluid behaves. We might be living in a cosmic moment where dark energy's strength is just right for life to exist, a fleeting equilibrium in an ever-changing cosmos. The search for quintessence isn't just about solving a puzzle. It's about discovering whether the universe is a static stage or a living, breathing entity with its own rhythm. And that's a revelation worth chasing. Imagine the universe in its infancy, a seething plasma so dense that light couldn't travel more than a hair's breadth before scattering. In this primordial soup, sound waves rippled outward like echoes in a cosmic canyon, compressing matter into peaks and valleys with astonishing regularity. Fast forward 13.8 billion years, and those ancient vibrations are still written in the stars, etched into the very arrangement of galaxies we see today. These frozen ripples, known as Baryonic acoustic oscillations, are the universe's way of handing us a ruler stamped with its own fingerprints. Here's how it works. Those early sound waves traveled at nearly 2/3 the speed of light until the cosmos cooled enough for atoms to form, freezing the waves in place like a snapshot. The result, galaxy clusters today are slightly more likely to be separated by a specific distance, about 500 million light-years, than any other. It's as if the universe left breadcrumbs in the form of a preferred spacing, a cosmic yardstick we can use to measure expansion across eons. Projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, DESI, map millions of galaxies to spot this telltale pattern, turning the sky into a grid of these ancient oscillations. But here's where it gets weird. When scientists compare these BAO measurements with supernova data, the numbers don't always line up perfectly. The universe's expansion rate seems slightly faster when measured with Baryonic oscillations than with distant stellar explosions. It's like using two different tape measures and getting conflicting lengths, except the tape measures are relics of the Big Bang. Some speculate this tension could hint at dark energy evolving over time, or even undiscovered particles altering gravity's rules. Others wonder if we're seeing the first cracks in our cosmological models, a sign that the Lambda-CDM framework might need tweaking. The real power of Baryonic acoustic oscillations lies in their cross-checking potential. Unlike supernova, which rely on the brightness of individual stars, BAOs trace the large-scale structure of the entire universe, offering an independent way to test dark energy's grip on cosmic expansion. Add in measurements from the cosmic microwave background and gravitational lensing, and suddenly we've got multiple lines of evidence all pointing toward, or occasionally contradicting, the same mind-bending conclusion. It's the scientific equivalent of triangulating a signal, narrowing in on the truth by seeing where all the data converges. What's thrilling is how these oscillations bridge the ancient and the modern. Those sound waves began their journey when the cosmos was a mere 380,000 years old, yet they're still guiding us today, helping unravel mysteries Einstein couldn't have dreamed of. And with every new galaxy survey, we're not just mapping space, we're replaying the universe's first notes, listening for the subtle harmonies that might reveal dark energy's deepest secrets. Think of the cosmic microwave background as the universe's first baby photo, a snapshot from when it was just 380,000 years old, still glowing from the heat of the Big Bang. This faint afterglow, now cooled to a mere 2.7 degrees above absolute zero, is more than a relic. It's a treasure map encoding secrets about dark energy in its subtle ripples and shadows. When the Planck satellite scanned this ancient light with unprecedented precision, it didn't just confirm the universe's age, it handed cosmologists a bombshell. Space on the largest scales is geometrically flat, not saddle-shaped, not spherical, but perfectly balanced like a taut sheet. And here's the catch: for that flatness to exist, something invisible had to make up the difference between the matter we see and the curvature we don't. That something, dark energy, filling the cosmic ledger to keep the books balanced. But the CMB's revelations don't stop there. Look closely at its temperature fluctuations, tiny hot and cold spots no larger than 1/100th of a degree, and you'll spot anomalies that defy expectations. Take the infamous cold spot, a sprawling region in the southern sky where the background radiation dips unusually low. Some theorists whisper this could be a bruise left by a collision with another universe during inflation. Others suggest it's evidence of dark energy interacting with space-time in ways we've yet to model. Either way, these quirks are like finding smudges on that baby photo, hints that the universe's early moments might have been messier or far stranger than we assumed. What makes the CMB such a powerful dark energy detective is its ability to freeze-frame the universe at two critical moments: its toddler phase as seen in the Baryonic acoustic oscillations, and its infancy in the microwave background. Comparing these snapshots lets scientists track how dark energy's influence has grown over billions of years. Planck's data, combined with measurements from ground-based telescopes like the Atacama Cosmology telescope, reveal a timeline where dark energy was once a background player, overshadowed by matter's gravitational pull. Only around 5 billion years ago did it emerge as the dominant force, kicking off the acceleration we see today. Now, a new generation of experiments is poised to scrutinize these clues with even sharper eyes. The Simons Observatory in Chile's high desert will map the CMB with tens of thousands of detectors, hunting for polarization patterns that might trace dark energy's quantum origins. Meanwhile, the CMB S4 project aims to spot primordial gravitational waves ripples that could reveal if dark energy was already at work during inflation, shaping the universe's expansion from its very first moments. These missions won't just test existing theories, they might uncover entirely new physics hidden in the static of the cosmos's oldest light. The beauty of the CMB is that it's both an endpoint and a starting line. It marks the instant the universe became transparent, but also the moment its deepest mysteries like dark energy's true nature were imprinted in light. Every new reading of this cosmic parchment brings us closer to understanding why the universe didn't just survive its fiery birth, but learned to run. And that's a story written in the afterglow of creation itself. For decades, the Hubble constant, the rate at which the universe expands, was considered one of cosmology's bedrock numbers. Lock it down and you'd have a key to the cosmos's age, size, and fate. But in recent years, something unsettling has emerged. Two of our most trusted methods for measuring this critical number refuse to agree. It's as if two identical clocks, both meticulously calibrated, started ticking at different speeds. Scientists call this discrepancy the Hubble tension, and it's not just a minor accounting error. It's a gaping 5 to 10% rift between how fast we think the universe is growing and what the data actually shows. On one side, we have local measurements using nearby supernova and pulsating stars called Cepheid variables. These cosmic yardsticks, honed over a century of observation, suggest the universe is expanding at about 73 kilometers per second per megaparsec. On the other side, calculations based on the cosmic microwave background, the afterglow of the Big Bang, point to a slower pace, around 67. That difference might sound small, but in a field where precision is everything, it's like discovering your GPS and paper map disagree on which continent you're standing on. The implications are profound. Either we're missing something fundamental in our measurements, or the laws of physics themselves need rewriting. One radical solution gaining traction is the idea of early dark energy, a fleeting surge of repulsive force that briefly turbocharged the universe's expansion in its first few 100,000 years. Picture a sprinter who bolts off the starting line too fast, then settles into a steadier pace. If this extra push happened, it would explain why the CMB predicts a slower expansion today, while local measurements catch the aftermath of that ancient speed boost. Others propose tweaking gravity itself, suggesting Einstein's equations might need adjustments on cosmic scales. Modified gravity theories, like emergent gravity or scalar tensor models, attempt to bridge the gap by reimagining how mass and energy curve spacetime. Then there's the wild card. What if the tension isn't a flaw in our models, but a fingerprint of something entirely unexpected? Could it hint at hidden dimensions, parallel universes leaking into ours, or even a cosmic unevenness where expansion rates vary across space? The Hubble tension forces us to confront an exhilarating possibility that we're on the verge of a breakthrough far bigger than dark energy itself. Every discrepancy in science is either a problem to solve or a doorway to walk through. And right now, cosmologists are standing at the threshold, wondering which one this will be. The stakes couldn't be higher. If the tension persists, it could mean that our understanding of the universe's infancy, its composition, or even the nature of time is fundamentally incomplete. Upcoming telescopes like the Vera-C, Rubin Observatory, and the James Webb Space Telescope are poised to sharpen these measurements, potentially turning today's confusion into tomorrow's revelation. What makes this moment so electrifying isn't just the mystery, it's the realization that the universe might still have a few tricks up its sleeve, waiting to surprise us when we least expect it. What if dark energy isn't the only explanation for cosmic acceleration? Some physicists are betting the real answer lies not in some mysterious force, but in a flaw in Einstein's theory of gravity itself. Enter modified gravity, a radical reimagining of how mass bends spacetime, where the rules we've trusted for a century might need a rewrite. The most famous contender is MUND, short for modified Newtonian dynamics, which suggests gravity behaves differently at extremely low accelerations, like those found in the outskirts of galaxies. Instead of invoking dark energy, MUND tweaks the math so that gravity's pull weakens less than expected over vast distances, creating the illusion of extra repulsive force. It's like realizing your car's speedometer was miscalibrated all along, no need for an invisible foot on the gas pedal. But MUND isn't alone. Theories like FR gravity take a different approach, adding new terms to Einstein's equations that kick in on cosmic scales, effectively mimicking dark energy's effects without requiring it. Picture a stretched rubber sheet that secretly thickens as it expands, altering how weights placed on it roll apart. These models can beautifully replicate the universe's accelerated expansion, but they hit a snag when faced with galaxy clusters. Observations show these massive structures bend light more strongly than modified gravity predicts unless you add, well, dark matter. It's a cosmic catch-22, tweak gravity to kill dark energy, and you might resurrect the need for another invisible ingredient. Gravitational waves could break the stalemate. When black holes collide, they send ripples through spacetime that carry clues about gravity's true behavior. Modified gravity theories predict these waves should interact subtly differently with the universe's expansion compared to Einstein's relativity. The LIGO and Virgo detectors are now hunting for these minute deviations, like listening for echoes in a hall where the walls might be made of something stranger than we thought. This brings us to black holes' gravity's ultimate laboratories. These cosmic vacuum cleaners don't just swallow light. They warp the fabric of reality around them, offering a front-row seat to how extreme gravity behaves. Recent simulations suggest that if modified gravity is correct, black holes might leave faint imprints in the way they spin or merge, signatures future telescopes could spot. Even stranger, some theories propose that black holes themselves could be leaking gravity into hidden dimensions, subtly altering how it propagates across the cosmos. The beauty of this debate is its audacity. It forces us to ask, are we missing something fundamental about the universe, or just seeing shadows of the equations we haven't finished writing? Whether dark energy or modified gravity wins out, one thing's certain: the answer will rewrite physics as we know it, and that's a discovery worth waiting for. In the shadowy hearts of galaxies, supermassive black holes have long been seen as cosmic destroyers, gravity's ultimate triumph where even light meets its end. But what if these monsters aren't just lurking in the dark? What if they're secretly fueling the universe's expansion? A bombshell 2023 study proposed exactly that, suggesting the energy within black holes might be the hidden source behind dark energy's relentless push. At first glance, it sounds like science fiction, yet the math tells a compelling story. The theory hinges on vacuum energy, the same quantum froth that physicists suspect might power the cosmological constant. Inside a black hole's event horizon, space-time warps so severely that quantum fluctuations could generate enormous repulsive pressure. Normally, this energy stays locked away, but the study argues that as black holes grow, their vacuum energy leaks into the wider universe, acting like a cosmic throttle pressing harder as more matter falls in. Picture a steam engine where the boiler is a black hole, and the exhaust is dark energy itself. The numbers even line up, tally the combined output of all supermassive black holes across cosmic history, and it neatly matches the observed acceleration rate. Not everyone's convinced. Critics point out glaring gaps, like why this mechanism wouldn't have triggered acceleration earlier in the universe's history, or how it accounts for dark energy's apparent uniformity across vast cosmic voids. Others argue the study conflates correlation with causation, noting that black holes and dark energy dominance arose around the same time without necessarily being connected. The loudest objection comes from general relativity purists, who maintain that black holes should act as perfect energy sinks, not secret fountains, yet the idea refuses to die. Follow-up simulations show intriguing hints that rotating black holes could indeed harbor vacuum states capable of influencing spacetime's expansion. Meanwhile, astronomers are racing to test the theory by studying ancient black holes in distant quasars. If their growth rates align with specific predictions, we might have our first clue that Einstein's monsters are cosmic architects in disguise. What makes this hypothesis so electrifying isn't just its audacity, it's the potential unification of physics' greatest puzzles. Black holes straddle the line between quantum mechanics and relativity, two theories famously at odds. If their vacuum energy truly drives cosmic acceleration, we'd be staring at a Rosetta Stone linking the very small to the very large. It's a long shot, but as one researcher put it, when the universe hands you a clue this juicy, you follow it. even if it leads into the abyss. Imagine living inside a cosmic bubble, not the kind that pops, but a vast, underdense region of space where galaxies are scarce and emptiness reigns. Some cosmologists think our entire observable universe might be nestled in such a void, a fluke of cosmic geography that's tricking us into believing in dark energy. This wild idea, known as the void energy hypothesis, suggests that what we've called acceleration could just be an illusion, a mirage created by our lopsided place in the cosmos. Picture the universe like a block of Swiss cheese, with dense clusters of galaxies as the cheese and enormous voids as the holes. If we're floating near the center of one of those holes, the surrounding emptiness would distort our view. Gravity behaves differently here. Less matter means weaker gravitational pull, so nearby galaxies would appear to recede faster than expected, mimicking the effects of dark energy's push. It's like standing in a valley and assuming the whole world slopes downward because you can't see the mountains beyond the horizon. The math behind this is surprisingly elegant. In a low-density bubble, the fabric of spacetime expands faster locally than in denser regions, creating a false signal of cosmic acceleration. Early simulations showed that if our bubble stretched at least 250 million light-years across, it could reproduce the supernova observations without invoking dark energy at all. But here's the catch: such a void would need to be improbably large, defying the statistical expectations of the standard cosmological model. It'd be like winning the lottery 10 times in a row, possible but staggeringly unlikely. Critics argue that voids this size should leave other imprints, like distinct patterns in the cosmic microwave background or skewed measurements of galaxy flows. Yet when astronomers scour the data, the evidence is murky. Some studies claim to spot hints of a local underdensity in galaxy surveys, while others find no deviation from uniformity. The debate rages on, fueled by tantalizing but inconclusive clues. Next-generation telescopes could settle the argument. Projects like the Vera-C Rubin Observatory will map billions of galaxies with unprecedented precision, hunting for telltale voids or irregularities in cosmic structure. If they find our neighborhood is truly special, it would upend decades of assumptions not just about dark energy, but about the fundamental fairness of the universe. After all, cosmology relies on the Copernican principle, the idea that we don't occupy a privileged place in space. A giant void would force us to confront the unnerving possibility that we're the exception, not the rule. Whether the void hypothesis holds up or not, it's a reminder of how carefully we must interrogate our cosmic assumptions. Sometimes the biggest mysteries aren't out there in the dark, they're hiding in plain sight, woven into the very fabric of our perspective. And that's a humbling thought. What if dark energy isn't just a steady push, but a force that ebbs and flows like cosmic tides? For years, the standard model treated it as a constant, Einstein's cosmological constant frozen in time. But new observations are chipping away at that assumption, revealing tantalizing hints that dark energy might be evolving, growing stronger or weaker as the universe ages. The evidence comes from some of the most distant beacons in the cosmos, quasars, the blazing cores of ancient galaxies powered by supermassive black holes. When astronomers analyzed light from quasars 7 to 12 billion years old, they found patterns in how their light stretched during its long journey to Earth. The data suggests dark energy's repulsive grip might have been subtly different in the universe's youth, less a fixed constant and more a dynamic player in cosmic history. Galaxy clusters add another layer to the puzzle. These massive knots of matter bound by gravity should grow denser over time as they pull in surrounding gas and galaxies. Yet when scientists measured the growth rates of clusters across cosmic epochs, they found them slightly stunted, as if an unseen hand was prying them apart more forcefully than expected. The discrepancy is small, but it lines up eerily with theories where dark energy strength creeps upward, resisting gravity's pull with increasing vigor. It's like trying to build a sandcastle as the tide rolls in faster and faster. Eventually, the waves win. Enter two groundbreaking missions designed to crack this mystery wide open: the Dark Energy Spectroscopic Instrument Decay and the European Space Agency's Euclid telescope. Decay is mapping over 40 million galaxies and quasars, creating a 3D atlas of the universe stretching back 11 billion years. By pinpointing baryon acoustic oscillations, those frozen sound waves from the early universe, it can track how dark energy's push has altered the spacing of galaxies over cosmic time. Euclid, meanwhile, is scanning billions of galaxies to measure their shapes. When light from distant galaxies warps around massive objects, a phenomenon called gravitational lensing, it betrays the distribution of both visible and dark matter. Combined, these datasets could reveal whether dark energy's strength is truly constant or drifting like a phantom current beneath spacetime. The stakes couldn't be higher. If dark energy is growing stronger, we might be headed toward a big rip scenario where galaxies, stars, and even atoms are torn apart. If it's weakening, the cosmos could eventually slow its expansion or even reverse it, collapsing in a big crunch. And if it's truly constant, that still leaves the haunting fine-tuning problem: why its value is so perfectly calibrated to allow life to exist. Every measurement from Decay and Euclid brings us closer to answering a question that sounds like science fiction but could redefine reality. Is the universe's acceleration itself accelerating? One thing's certain: the cosmos refuses to sit still. Whether dark energy is a steady hand or a shape-shifting enigma, its secrets are etched in the light of quasars, the sprawl of galaxy clusters, and the echoes of sound waves from the dawn of time. And with each new dataset, we're not just reading the universe's past, we might be glimpsing its ultimate fate. Among the universe's most elusive particles, neutrinos have long been ghosts whizzing through planets and stars almost unnoticed, barely interacting with matter. But these tiny cosmic speedsters might hold surprising sway over the universe's expansion. For decades, physicists assumed neutrinos were massless, but groundbreaking experiments like Japan's Supermassive and the Sudbury Neutrino Observatory shattered that belief, proving they have a whisper of mass. While each neutrino is staggeringly lightweight, at least 500,000 times lighter than an electron, their sheer numbers add up. Trillions pass through you every second, relics of the Big Bang and nuclear reactions in stars. Collectively, they could exert enough gravitational influence to nudge cosmic expansion in ways we're only beginning to understand. One provocative theory suggests neutrinos might be secretly entangled with dark energy. In some models, their masses aren't fixed but vary as the universe expands, subtly altering how they interact with spacetime. Picture a cosmic seesaw. As neutrinos lose energy over billions of years, they could transfer it to dark energy, amplifying its repulsive push. It's a delicate dance, one that might explain why dark energy's dominance coincided roughly with the era when neutrinos slowed down enough to affect large-scale structure. The math is speculative but tantalizing. If true, it would mean these overlooked particles are cosmic puppeteers, quietly shaping the fate of everything. Enter IceCube, the Antarctic observatory buried deep in glacial ice, hunting high-energy neutrinos from cataclysms like colliding black holes and supernova. By analyzing these messengers from across the cosmos, scientists are piecing together how neutrino behavior changes over astronomical distances, clues that could reveal their role in dark energy's grip on the universe. Already, IceCube has spotted neutrinos with energies 1,000,000 times greater than those from particle accelerators, some possibly forged in the same violent events that seed galaxy clusters. If certain neutrino types interact differently with dark energy, their fingerprints might be hidden in these extreme events, but the plot thickens when dark matter enters the picture. These two invisible cosmic players, neutrinos and dark matter, might be more connected than we thought. Some theories propose that dark matter particles occasionally decay into neutrinos, or that they interact via undiscovered forces. Others suggest neutrinos could mediate how dark matter clumps together, subtly altering the universe's scaffolding. It's a three-way tug of war: dark energy pushing space apart, dark matter pulling it together, and neutrinos threading through both, possibly tipping the balance. The implications are dizzying. If neutrinos influence dark energy's strength, or if dark matter decays into them, it could mean the universe's expansion isn't just a story of gravity versus repulsion. It's a symphony of invisible particles, each playing its part across billions of years. And with every new neutrino detected in Antarctic ice or galactic debris, we're decoding notes from that symphony, inching closer to understanding why the cosmos accelerates at all. Dark matter has always been the universe's silent partner, an invisible scaffold shaping galaxies and clusters through gravity alone. But what if it's not just a passive player? New simulations reveal a startling possibility. Dark matter might be whispering directly to dark energy, fueling cosmic acceleration in ways we never imagined. Picture this: an entire dark sector of particles and forces, hidden from our telescopes but orchestrating the universe's expansion behind the scenes. Some models suggest dark matter could slowly decay into dark energy, like a cosmic battery discharging its energy into the void. Others propose the two interact via undiscovered forces, exchanging influence like shadowy partners in a dance we're only beginning to trace. Take galaxy rotation curves, for example. For decades, we've known stars orbit galactic centers too fast to be held by visible matter alone, the classic evidence for dark matter's gravitational grip. But recent observations reveal odd quirks in these rotations, small inconsistencies that the standard dark matter model can't quite explain. Some galaxies spin slightly faster or slower than predicted, as if an unseen hand is tweaking gravity's rules. Could these anomalies be hints of dark matter interacting with dark energy? Supercomputer simulations say maybe. In virtual universes where dark matter particles decay or exchange energy with dark energy, similar quirks emerge in galactic behavior. It's like finding fingerprints at a crime scene that match a suspect no one knew to look for. The most provocative theories go even further. Imagine dark matter isn't a single substance but a family of particles, some of which transform into dark energy over cosmic time. Early in the universe, these particles would have behaved like classic dark matter, clumping together to form gravitational wells for galaxies. But as space expanded, a fraction might have melted into dark energy, gradually shifting the balance from attraction to repulsion. This could explain why cosmic acceleration kicked off relatively late. Dark matter had to decay enough to tip the scales. Then there's the Bullet Cluster, one of astronomy's most famous cosmic collisions. When two galaxy clusters smashed together, their dark matter detected via gravitational lensing and hot gas became separated, proof dark matter exists. But subtle asymmetries in the debris might hide deeper secrets. Some researchers argue the dark matter's distribution is slightly off from predictions, as if it experienced extra pressure or push during the collision. Could that pressure be dark energy's influence, a shadowy interaction playing out on scales we're only now learning to measure? upcoming experiments like CERN Forward Search Experiment Phaser and the Vera-C. Rubin Observatory could shine light on these dark sector theories. Phaser hunts for hypothetical dark photons that might mediate forces between dark matter and energy, while Rubin's ultra-deep sky surveys will spot more galactic anomalies that could betray these hidden connections. Every odd rotation curve or unexpected lensing pattern might be a breadcrumb leading to a radical rewrite of cosmic history, one where dark matter isn't just the universe's hidden skeleton, but the spark that ignited its accelerating fate. The beauty of this idea isn't just its audacity, but its elegance. For years, we've treated dark matter and dark energy as separate puzzles, each confounding in their own way. But if they're two faces of the same cosmic coin, the pieces might finally start falling into place, and that's a revelation worth chasing into the dark. Quantum entanglement isn't just a laboratory curiosity. It might be the invisible glue stitching the cosmos together. Picture two particles separated by billions of light years, instantly influencing each other's states as if space and time don't exist. Now imagine this spooky connection isn't rare, but woven into the fabric of reality itself, a cosmic tapestry of entangled particles stretching across the universe. Some theorists believe this web of quantum connections could hold the key to dark energy's mystery, turning empty space into an engine of cosmic acceleration. The idea hinges on vacuum energy, the seething quantum foam where particle pairs constantly blink in and out of existence. Normally, these fleeting particles cancel each other out, but entangled pairs leave faint imprints on spacetime. Recent quantum gravity models suggest these imprints could add up to a repulsive force on cosmic scales, like trillions of microscopic springs pushing space apart. Think of it this way: every cubic centimeter of empty space might contain a network of entangled links, each one subtly straining against the fabric of the universe. Over billions of light years, that strain could become the driving force behind dark energy's relentless push. One groundbreaking paper from the Perimeter Institute calculated that if even a fraction of the vacuum's entanglement energy remains uncancelled, it could precisely match the observed strength of dark energy. The math is speculative, but tantalizing, like finding a hidden equation scribbled in the margins of reality. Even stranger, this theory suggests dark energy isn't a static force, but a dynamic echo of the universe's quantum underpinnings. As space expands, new entanglement connections form, threading the growing void with fresh repulsive potential. It's as if the cosmos is constantly weaving its own expansion mechanism, stitch by quantum stitch. But how do we test something so abstract? Enter the holographic principle, a radical idea from string theory suggesting the universe's information might be encoded on a distant two-dimensional surface. If true, entanglement could be the mechanism projecting that information into our 3D world, with dark energy emerging as a side effect. Experiments like the holometer at Fermilab are already hunting for telltale quantum fuzziness in spacetime, tiny fluctuations that could betray this hidden entanglement layer. Meanwhile, astronomers are scouring quasar light for anomalies that might reveal entangled links across cosmic voids. The implications are staggering. If entanglement fuels dark energy, it would mean the universe isn't just expanding, it's alive with quantum conversations we're only beginning to overhear. From the tiniest particles to the vast cosmic web, everything might be connected by threads we can't see, pulsing with energy we're just learning to measure. And that's a thread worth pulling. What if everything we see, every galaxy, every star, even the space between them, is nothing more than a cosmic mirage? The holographic principle turns this wild idea into serious physics. suggesting our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface. Picture a movie screen where the depth, movement, and drama all emerge from flat pixels. Now imagine the entire cosmos works the same way, with dark energy as the unexpected byproduct of this grand illusion. This mind-bending concept stems from black hole physics. When scientists calculated how much information a black hole can hold, they found it's proportional not to its volume, but to its surface area. That bizarre result led to a radical proposal. Maybe all the information in any region of space, including the universe itself, is stored on its boundary. The AD/S/CFT correspondence, a mathematical bridge between string theory and quantum field theory, gives this idea teeth. It shows how a higher dimensional space, like our universe, can perfectly mirror the physics of a lower dimensional world, like a hypothetical 2D surface at the edge of reality. So where does dark energy fit in? If the universe is holographic, its expansion could be linked to how information spreads across that boundary. Some models suggest dark energy's value isn't arbitrary, it's mathematically locked to the amount of information the cosmos can encode. Think of it like a cosmic pixel limit. As the universe grows, new pixels of space emerge, but the total information density stays constant, generating a repulsive force that drives acceleration. It's as if the universe is running out of memory and stretching itself thin to compensate. The implications are staggering. A holographic cosmos would mean dark energy isn't some exotic substance, but a side effect of reality's deepest structure. Even stranger, this framework could solve the infamous cosmological constant problem: why dark energy's measured value is so tiny compared to theoretical predictions. In a holographic universe, quantum fluctuations might naturally cancel out at large scales, leaving behind just the faint whisper we detect as dark energy. Experiments are already hunting for clues. Gravitational wave detectors could spot subtle anomalies in spacetime's fabric, signatures of hidden dimensions or information limits implied by holography. Meanwhile, quantum computers simulate toy universes to test how well lower dimensional systems mimic higher dimensional physics. Every glitch or pattern in these simulations might be a breadcrumb leading us closer to the truth. Whether the holographic principle holds up or not, it's a reminder of how deeply interconnected physics' greatest puzzles might be. Dark energy, black holes, quantum gravity, they could all be threads in the same cosmic tapestry, woven from information we're only beginning to decode. And that's a mystery worth unraveling. What if dark energy's perplexing value isn't a cosmic accident, but a roll of the dice in a multiverse casino? Among the most controversial explanations for dark energy's fine-tuning is the idea that our universe is just one bubble in an infinite froth of realities, each with different physical constants. In this sea of possibilities, most universes might have too much dark energy, ripping themselves apart before stars can form, or too little, collapsing instantly. Ours, by sheer chance, landed in the narrow sweet spot where galaxies and life could emerge. It's the ultimate Goldilocks scenario, not too strong, not too weak, but just right. This anthropic reasoning divides scientists like few other topics. Supporters argue it's the only way to explain dark energy's improbable balance without invoking divine intervention or undiscovered physics. Critics fire back that it's a philosophical cop-out, a way to dodge the hard work of finding a deeper mechanism. The debate cuts to the heart of what science should be: a search for testable explanations or a broader meditation on why the universe is hospitable to questions at all. But the multiverse isn't purely speculative. Certain versions of string theory predict a landscape of bubble universes, each with different laws of physics. Inflation, the rapid expansion of the early cosmos, could have spawned countless such bubbles, making our universe one of many. Even wilder, some models suggest these bubbles might collide, leaving scars in the cosmic microwave background, subtle temperature variations that next-generation telescopes could detect. The European Space Agency's Euclid mission is already scanning for these fingerprints, while tabletop experiments hunt for gravitational anomalies that might hint at hidden dimensions. The stakes are cosmic. If the multiverse is real, dark energy's value isn't a puzzle to solve but a lottery ticket we happen to hold. Yet, even if true, it raises thornier questions. Could we ever observe other universes, or are they forever beyond our reach? And if the multiverse is unfalsifiable, incapable of being disproven, does it belong in science at all? For now, the multiverse remains a tantalizing what if. But as experiments push deeper into the quantum realm and the cosmos's farthest edges, we might find that the answer to dark energy's mystery lies not in our universe alone, but in the shimmering vastness of all possible worlds. Wormholes aren't just science fiction. They could be cosmic shortcuts hiding in the equations of general relativity. Einstein himself, working with Nathan Rosen, theorized these space-time tunnels as bridges connecting distant points in the universe. But there's a catch. Keeping a wormhole stable requires something bizarre called exotic matter, a substance with negative energy that defies gravity's pull. Sound familiar? It's eerily similar to the repulsive force we call dark energy, almost as if the universe handed us a clue wrapped in a paradox. Exotic matter isn't your average cosmic ingredient. Picture a material so strange, it bends space-time inward like a cosmic trampoline, propping open a wormhole's throat against collapse. Theoretically, it could be laced with negative mass, making it fall up instead of down. While we've never observed such matter directly, quantum mechanics offers a tantalizing loophole. The Casimir effect, where two metal plates in a vacuum experience an invisible force pushing them together, hints at regions of negative energy density, a ghostly echo of what wormholes might need. It's as if the quantum realm is whispering, "Here's your exotic matter, just assemble it right. Now tie this to one of physics' most audacious ideas, equals EPA." Proposed by Leonard Susskind and Juan Maldacena, this conjecture suggests that wormholes' Einstein-Rosen bridges, or might be the same as quantum entanglement, Einstein-Podolsky, Rosen, or EPA. In other words, two entangled particles could be connected by a microscopic wormhole, a quantum bridge threading space-time itself. If true, it would mean the universe's spookiest phenomenon, entanglement, is literally weaving its fabric with tunnels we can't yet see. Dark energy, with its repulsive grip, might even play a role in stabilizing these structures, like cosmic glue for hidden highways. But how do we hunt for something so elusive? Enter LIGO, the gravitational wave observatory that's already revolutionized astronomy. While it wasn't built to detect wormholes, its precision could uncover anomalies hinting at their existence. Imagine two black holes merging, but their gravitational waves carry faint echoes, ripples that suggest their collision briefly warped space-time into a tunnel. Or consider a star's light flickering strangely as it passes near an invisible throat in space. These signatures would be subtle, but LIGO successors, like the planned LISA Space Observatory, might just catch them. The wildest twist: if wormholes threaded with exotic matter exist, they could be leaking dark energy into our universe, subtly influencing its expansion. It's a long shot, but in a cosmos where black holes sing and empty space pushes galaxies apart, perhaps the most outlandish ideas are the ones we should take seriously. After all, reality has a habit of outdoing our wildest imaginations, one wormhole at a time. Deep in the fabric of space-time, there might be cracks, ancient scars from the universe's violent birth, stretching across billions of light years like invisible wires under tension. These are cosmic strings, hypothetical defects in the structure of reality itself, theorized to have formed when the young cosmos underwent a phase transition, like ice crystals forming in freezing water. But unlike ice, these cracks wouldn't melt. They'd persist, thinner than a proton but denser than a mountain range, vibrating with the energy of the Big Bang. And here's the wild part. Some scientists think these strings could be secretly tugging the cosmos apart, acting as hidden engines of dark energy. Picture a cosmic string as a flaw in spacetime's weave, so massive that just 1 centimeter of it could weigh as much as the entire Earth. If such a string passed through our solar system, we might not even notice except for the way it would warp the light of distant stars, bending their images into strange, mirrored pairs. Astronomers call this gravitational lensing, and it's our best hope for spotting these elusive relics. Teams using telescopes like Hubble and the upcoming Vera-C. Rubin Observatory are scanning the skies for these subtle distortions, hunting for the telltale flicker of a string's passage. So far, no definitive detections, but the search is far from over. What makes cosmic strings such compelling dark energy candidates is their bizarre physics. Unlike black holes or galaxies, they wouldn't just curve space-time, they'd twist it. Some models suggest that as strings vibrate or intersect, they could release bursts of energy into the vacuum of space, adding to the repulsive force we call dark energy. It's like plucking a guitar string and hearing not sound, but the faint hum of expansion itself. Even more intriguing, if strings looped back on themselves, they might collapse into miniature black holes, seeding the cosmos with dark matter in the process. The real magic lies in their potential to solve multiple cosmic riddles at once. If strings exist, they could explain why the universe's expansion seems so uniform. Like invisible puppet masters, their vast networks might be pulling spacetime apart with eerie consistency, leaving no region untouched. They might even account for the universe's missing magnetic monopoles, theoretical particles predicted by grand unified theories but never observed. Strings could have soaked them up like cosmic sponges, hiding them in the folds of spacetime. Yet the biggest question remains, are these strings even real? The math says they could be, but nature isn't obligated to follow our equations. Some theories, like string theory, suggest cosmic strings are inevitable dimensional frayings left over from higher dimensional physics. Others argue they'd have decayed long ago, vanishing in a burst of gravitational waves. The answer might lie in the faint tremors of the universe itself. Gravitational wave detectors like LIGO could one day catch the echoes of a snapping string, a ripple in spacetime carrying the signature of a defect older than the stars. Whether cosmic strings are out there or not, their possibility reminds us how much of the universe is still written in riddles. They're threads in a grand cosmic tapestry, woven from the same mysteries as dark energy itself. And if we ever find them, it won't just be a discovery, it'll be a glimpse into the universe's first moments, when reality was still stitching itself together. There's a haunting possibility lurking in the equations of quantum physics, one that makes black holes and phantom energy seem almost comforting by comparison. Imagine the very fabric of reality is perched on a knife's edge, not in some distant galaxy, but right here, right now, beneath your feet. This is the vacuum decay catastrophe, a scenario where our universe isn't the stable cosmic home we assume, but a precarious bubble in a false vacuum state, one quantum fluctuation away from annihilation. At the heart of this nightmare is the Higgs field, the invisible energy ocean that gives particles their mass. Most of the time, it behaves like a ball resting at the bottom of a valley, a stable, low-energy state. But theoretical models suggest this valley might not be the deepest possible. Somewhere beyond our perception, there could be a chasm, a true vacuum state with far lower energy. If quantum tunneling allows the Higgs field to roll down into that abyss, it would trigger a shockwave of restructuring at the speed of light, rewriting the laws of physics as it expands. Atoms would disintegrate, forces would unravel, and the universe as we know it would cease to exist in an instant. What makes this especially eerie is dark energy's potential role. If our vacuum is metastable, just stable enough to last billions of years, but not eternally, then dark energy's repulsive push might be the faint tremor before the avalanche. Some theories propose that dark energy's value, which seems suspiciously fine-tuned for life, could be a temporary artifact of this unstable equilibrium. Like a house of cards standing just long enough for us to marvel at it before collapsing, the hunt for clues has led physicists to the Large Hadron Collider, where precise measurements of the Higgs boson's mass could reveal whether our vacuum sits on shaky ground. So far, the data suggests we're probably safe. The Higgs mass aligns with a metastable universe, but one that could persist for far longer than its current age. Probably, the margin of error isn't zero, and if a single high-energy cosmic event, say, a black hole merger or a quantum fluctuation in a distant galaxy tipped the scales, the resulting phase transition would be unstoppable. No alarm, no time to react. One moment, the universe, the next, a void governed by entirely alien rules. Yet there's a strange beauty in this fragility. It forces us to confront how delicately the cosmos is balanced, and how much we still don't understand about the ground beneath our feet, literally. Whether vacuum decay is a real threat or just a mathematical curiosity, it's a reminder that the universe's greatest mysteries aren't always out among the stars. Sometimes they're hiding in the empty space between them. Now let's tackle one of the wildest twists in the cosmic acceleration saga. The idea that what we're seeing isn't dark energy at all, but something far more outlandish. Picture this, a network of alien megastructures, vast enough to block the light of distant supernova, throwing off our measurements and tricking us into believing the universe is speeding up. Or maybe it's just a glitch, a systematic error in telescope calibration, quietly warping the data for decades. These fringe theories might sound like sci-fi, but they're a fascinating reminder of how anomalies push science to its creative limits. Start with the Dyson sphere hypothesis. The notion that advanced civilizations could build massive energy-harvesting structures around stars isn't new. Physicist Freeman Dyson first floated the idea in the 1960s. But could swarms of these megastructures scattered across galaxies dim the light of supernova just enough to mimic cosmic acceleration? On paper, it's not impossible. If aliens were blocking, say, 1% of the light from every distant supernova, it might look like those explosions are farther away than they truly are, creating the illusion of accelerating expansion. The catch, we're talking about structures so numerous and perfectly placed, they'd need to outnumber stars in some galaxies. Even then, they'd leave other fingerprints, unnatural infrared heat signatures or strange patterns in starlight, none of which we've found. Then there's the simpler explanation, human error. Could subtle flaws in telescope optics or supernova models be skewing the data? Early critics pointed to potential calibration issues, dust in distant galaxies reddening starlight, or variations in supernova brightness that weren't fully accounted for. But over 2 decades, those concerns have been hammered out. Independent methods, baryon acoustic oscillations, galaxy clustering, even the cosmic microwave background, all converge on the same accelerating universe. The odds that every single technique shares the same systematic error, vanishingly small. Here's where Occam's razor slices through the noise. The simplest explanation, a mysterious energy inherent to space itself, might be unsettling, but it doesn't require unseen alien empires or a conspiracy of faulty instruments. Yet there's value in these fringe ideas. They force scientists to double-check assumptions, to ask, what if we're missing something obvious? After all, some of history's biggest breakthroughs started as heresies. The key is balance, entertaining wild possibilities without losing sight of the evidence. So while Dyson spheres make for thrilling storytelling, the real story is how science self-corrects. Every claim, no matter how exotic, gets stress-tested against data, and in this case the data keeps whispering the same strange truth. The universe really is accelerating, with or without aliens. But who knows, maybe somewhere in the cosmos, a civilization is pondering the same mystery, looking up at their night sky and wondering what's pushing it all apart. The next chapter in our cosmic detective story is already unfolding, with telescopes of unprecedented power preparing to hunt dark energy's elusive fingerprints. Leading the charge is Euclid, the European Space Agency's dark energy hunter, armed with a billion-pixel camera capable of mapping billions of galaxies across 10 billion light-years of cosmic history. Unlike traditional telescopes that focus on individual objects, Euclid will scan vast swaths of sky, measuring how galaxies cluster and bend light, subtle distortions that betray dark energy's grip on spacetime. But here's the genius twist. It'll also peer into the infrared spectrum, piercing through cosmic dust to spot ancient galaxies whose light has been stretched into invisibility by the universe's expansion. These redshifted relics could reveal how dark energy's strength has changed over epochs, settling the debate over whether it's truly constant or evolving. NASA's Nancy Grace Roman Space Telescope, launching later this decade, takes a different approach. Dubbed the Super Hubble, it'll conduct a galactic census 1,000 times larger than its famous predecessor, capturing detailed spectra of millions of supernovae and quasars. What makes Roman revolutionary is its ability to measure both the universe's expansion rate and how that rate has changed, a cosmic speedometer tracking acceleration across time. One especially clever trick, using Type Ia supernova not just as distance markers but as standard clocks. By analyzing how quickly these explosions brighten and fade at different distances, Roman could detect subtle shifts in dark energy's behavior, like a detective timing echoes in a cavern to map its hidden dimensions. Then there's the Square Kilometre Array SCAR, a radio telescope so vast its antennas will span continents from Australia to Africa. SKA's secret weapon is 21-centimeter hydrogen, mapping tuning into the faint radio whispers of neutral hydrogen atoms that pervade the cosmos. These primordial clouds, untouched since the universe's youth, form a cosmic web that dark energy has been stretching for eons. By comparing this web's structure across cosmic time, SKA could reveal whether dark energy warps spacetime uniformly or leaves telltale wrinkles in the distribution of matter. It's like examining the cracks in an expanding balloon to deduce the pressure inside. But perhaps the most exotic dark energy probe isn't a telescope at all. It's the growing network of gravitational wave observatories. When black holes collide, they send ripples through spacetime that carry precise distance information. By pairing these standard sirens with traditional redshift measurements, scientists can track the universe's expansion with unparalleled precision. Future upgrades to LIGO and Virgo, plus the upcoming LISA space antenna, could detect mergers from the universe's first billion years, clues to whether dark energy was already at work during cosmic infancy. Some theories even suggest gravitational waves might travel slightly differently through dark energy-dominated space, a potential smoking gun for modified gravity theories. What makes this new era so thrilling isn't just the technology, but the convergence of methods. Euclid's galaxy maps, Roman's supernova, SKA's hydrogen webs, and LIGO's spacetime ripples will cross-check each other, leaving dark energy fewer places to hide. If current theories survive this scrutiny, we'll have unprecedented confidence in our cosmic model. But if discrepancies emerge, if the data from these missions refuses to line up, we might be staring at the next physics revolution. Either way, the universe's greatest mystery is about to meet its match. While humans have spent centuries gazing at the stars, we're now training artificial eyes to see what we've missed: machines that can sift through cosmic noise to find the faint signals of dark energy's handiwork. Modern astronomy generates more data in a single night than researchers could process in a lifetime. From galaxy surveys mapping millions of light sources to gravitational wave detectors recording spacetime's faintest tremors. That's where AI steps in, not as a replacement for human curiosity, but as a powerful ally in our quest to decode the universe's acceleration. Take the Dark Energy Survey, for example, a project that captured images of 300 million galaxies across 1/8 of the sky. When scientists fed this colossal dataset into neural networks, the algorithms spotted subtle clustering patterns in galaxy distributions that hinted at dark energy's influence with precision no manual analysis could match. What makes machine learning so revolutionary isn't just its speed, but its ability to find connections we wouldn't think to look for. In Switzerland, physicists at CERN trained AI on particle collision data and watched in astonishment as it flagged anomalies that could point to entirely new particles, potential dark matter candidates, or even carriers of dark energy's force. These algorithms don't just follow pre-programmed rules. They teach themselves to recognize complex correlations, like cosmic detectives piecing together a puzzle with trillions of fragments. Some models have even predicted the existence of hypothetical particles called actions, which might interact with both dark matter and dark energy in ways that could solve multiple cosmic riddles at once. Yet the most profound implication of AI's cosmic sleuthing isn't just about new discoveries, it's reshaping how we ask questions. For decades, cosmology followed a linear path: observe, hypothesize, test. Now, machine learning can reverse engineer that process, mining data for patterns first and generating hypotheses afterward. It's like having a telescope that not only shows you distant galaxies but whispers ideas about why they're arranged that way. When Berkeley researchers fed quantum field equations into an AI system, it spontaneously suggested modifications to gravity theory that aligned eerily well with observed cosmic acceleration, proposals no human physicist had previously considered. This partnership between human intuition and artificial intelligence raises philosophical questions as deep as the cosmos itself. Are we building tools to extend our understanding, or are we creating successors that will eventually outthink our cosmic inquiries? Could an AI trained on enough universal data one day grasp dark energy's true nature while we're left straining to comprehend its conclusions? The irony is rich. We're using the most advanced technology born from human ingenuity to study phenomena that may predate humanity by billions of years. Perhaps the ultimate lesson lies not in the answers we find, but in recognizing how small our unaided perspective truly is against the vast, accelerating canvas of spacetime. Among the countless galaxies racing away into the void, we find ourselves perched on a fragile speck, witnessing an unfolding cosmic drama that may one day erase all traces of our existence. The revelation of cosmic acceleration doesn't just rewrite physics textbooks, it forces us to confront humanity's fleeting moment in a story stretching across billions of years. Picture this: every civilization that ever was or will be might exist within a narrow sliver of cosmic time, a brief window where the universe remains large enough to spark curiosity but small enough to still be explored. We've arrived just in time to glimpse the last visible chapters of the cosmic saga before the stars vanish beyond an unreachable horizon. This realization reshapes what it means to be a thinking species in an expanding cosmos. For centuries, we imagined the universe as an eternal, unchanging stage, a backdrop against which human history played out. Now we know better. The galaxies we see tonight are already ghosts, their light a message from a past when the cosmos was younger, denser, and more connected. In 1 trillion years, any astronomers left in our Milky Way will peer into a night sky nearly empty of galaxies, their light stretched beyond detection by dark energy's relentless push. The universe will appear static and solitary, with no evidence of the grand cosmic web we now observe. Our era, this sliver of cosmic history when galaxies still shine and mysteries remain within reach, might be the only time when intelligent life could glimpse the full grandeur of creation before the curtain falls. Yet there's a paradoxical beauty in this loneliness. The same acceleration that threatens to isolate us also makes our moment uniquely precious. We're living through the last cosmic epoch where the universe's history is still legible, like stumbling upon an ancient library just before its books turn to dust. Every observation we make, from the afterglow of the Big Bang to the dance of distant galaxies, is a snapshot of a fleeting equilibrium between gravity's pull and dark energy's push. Future civilizations might inherit a cosmos too fragmented to ever reconstruct its origins, making our current efforts to map the universe not just science, but a form of cosmic archaeology, a rescue mission against time itself. This raises profound questions about meaning in an accelerating cosmos. If the universe is destined for eternal expansion, does that render human achievement insignificant? Or does it amplify the extraordinary luck of our timing, that we emerged when the night sky still held answers? Some philosophers argue that dark energy's dominance might even be a prerequisite for life, as an earlier collapse or slower expansion could have prevented the formation of stable galaxies altogether. In this view, we're not just observers of cosmic acceleration, but its unlikely beneficiaries, living proof that the universe's apparent indifference might conceal a delicate balance enabling existence. Perhaps the greatest lesson lies in what we don't yet understand. The same mystery driving galaxies apart also binds us to the cosmos in a shared quest for comprehension. Every measurement of receding supernova, every map of galaxy clusters, every gravitational wave detected is a conversation with the universe, a way of asking, "What are you?" Across the vastness of space and time, dark energy might one day carry away the stars, but it can't erase the wonder that drives us to chase them. And in that pursuit, we're not just studying the universe, we're learning what it means to be alive within it. From the shocking revelation that the universe's expansion is speeding up to the bizarre possibility that black holes might be leaking dark energy, these 24 discoveries have rewritten the cosmic rulebook. Each one is a thread in a grand tapestry, supernova acting as cosmic mile markers, the eerie fine-tuning of the cosmological constant, the haunting specter of phantom energy dragging us toward a big rip. We've seen how quantum entanglement might stitch spacetime together, how cosmic strings could be vibrating with the energy of the Big Bang, and even how our entire universe might be a holographic projection. The deeper we dig, the stranger it gets. Multiverses where dark energy's value is a cosmic roll of the dice, wormholes threaded with exotic matter, and the terrifying fragility of our vacuum's stability. Yet for all we've uncovered, the puzzle is far from complete. Every answer births new questions. Is dark energy truly constant, or is it evolving, silently gaining strength like a gathering storm? Could modified gravity append everything we think we know, or will future telescopes catch dark matter decaying into the very force pushing the cosmos apart? The beauty of this mystery is its stubborn refusal to be boxed in. Just when we think we're closing in on the truth, the universe throws us a curveball. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That sentiment captures the heart of this quest. We're standing at the edge of discovery, peering into the dark with tools and minds sharp enough to glimpse the impossible. Maybe the answer lies in data already collected, waiting for the right perspective to reveal it. Or perhaps it's hiding in the next gravitational wave signal, the next supernova's flicker, the next quantum fluctuation in some lab's vacuum chamber. So tell us which of these theories sends your mind spinning: the holographic universe, black holes as dark energy factories, or something even wilder we didn't have time to cover. Drop your thoughts in the comments, and if you're itching for more cosmic deep dives, hit subscribe. The universe isn't done surprising us, and neither are we. After all, the greatest discoveries often start with a simple question: what if?